In this video, we want to look at inductor and inductance. At the end of this class, you will know what inductor and inductance is all about, types of inductance, application of inductors, and magnetic field energy. What is an inductor? An inductor is simply a coil of wire. Coil of wire, for instance, this is an inductor. You have a coil of wire, a conductive wire that you wrap across a core. So an inductor is simply a coil of wire, as we can see here. Then an inductance is the tendency of an electrical conductor to oppose a change in the electric current flowing through it. So that tendency of an electrical conductor to oppose a change in the electric current flowing through it is called an inductance. An inductance is the measure of opposition to the change in current, just like resistance is a measure of opposition to current. We have known before that resistor oppose the flow of current. So resistance, the measure of that opposition from resistor is called resistance. Then the tendency of a conductor to the flow of current through it is called an inductance. So an inductance and resistance, they are not the same. Resistance from a resistor, inductance from an inductor. The SI unit of inductance is Henry, named after the scientist that discovered this. There are two types of inductance. We have the self-inductance and we have the mutual inductance. Let's look at each of them. Self-inductance. Self-inductance is the ability of a conductor to induce voltage in itself when the electric current flow through it changes. Here is a circuit diagram of a coil and current flowing through it. So the ability of this coil to induce current in itself is what we call self-inductance. According to Faraday's law, that the induced EMF is given by equation 1. In one of our videos, we looked at electromagnetic induction. From there, you can get more information about Faraday's law. Then the number of turns in the coil is proportional to the current that is flowing through it. So the number of turns times the change in magnetic flux is proportional to the current. So from here, if we remove the constant of proportionality and introduce the constant L, which is our inductance, we will have equation 2. And if we simplify, making inductance subject formula, we have equation 3. Our L is the constant as explained area. So if we substitute Li into equation 1, we will have equation 4, which is the expression that the induced EMF is equal to the negative of the inductance times the rate of change of current in the coil. Let's look at mutual inductance. Mutual inductance is the ability of a coil to induce EMF in the nearby coil when the current in the first coil changes. As we can see here, we have two coils, A and B. If the current in A changes, it can induce EMF in coil B, and this will be detected by the galvanometer. The reverse is also possible. That is, the second coil can also induce an EMF in the first coil when the current in the second coil changes. This ability of reciprocal induction is measured in terms of coefficient called mutual induction. Let's consider two coils, A and B. if N2 psi magnetic flux of the second coil in respect to the first coil, which is the total flux linkage in coil B, then we can apply the same procedure we use for self-inductance, and we'll get the mutual inductance of the second coil with respect to the first coil to be equal to the number of turns in the second coil, magnetic flux in the second coil with respect to the first coil, over the current flowing in the first coil. This is given in equation 5. Then, according to Faraday's law, the induced EMF in coil B, the second coil, due to the changing current in coil A, is given by equation 6. And if we simplify further, we will have equation 7, which is the induced EMF in coil B with respect to the rate of change of current in coil A. Similarly, if coil B carry a time-varying current, EMF will be induced in coil A, and we will have the EMF given as equation 8. From equation 7 and 8, we have the induced EMF in coil B and coil A, respectively. An important property of the mutual inductance is that the mutual inductance in coil B with respect to coil A is equal to that of coil A with respect to coil B, which is equal to M. So replacing M, the mutual inductance here and this with M, will have our equation 10, which is the expression we can use to calculate the mutual inductance in coil B with respect to the rate of change of current in coil A, or the mutual inductance in coil A with the rate of change of current in coil B. Let's look at factors that affect inductance. These are different coils of different sizes, shape. So the first factor is the number of wire turns in the coil. Inductance increases with increase of the number of turns of wire in the coil. As we can see, these are inductors, these are the number of turns, as we can see here. The second factor is the coil area. Inductance is proportional to the coil area, meaning as the coil area increases, the inductance also increases. Another factor is the core material. Look at this. This is an inductor. You have the conducting wire, you have the cylindrical core. So the greater the magnetic permeability of the core to which the coil is wrapped around, the greater the inductance. So the core of material affects the inductance that is being produced. Then the coil length. The longer the coil's length, the lower the inductance. So the coil length is inversely proportional to the inductance. As we can see here, these are inductor of different sizes and shape. As we can see, the coil is not all that long, because the longer the coil, the lower the inductance. So these are the factors that affect inductance in the circuit. Then let's look at application of inductors. Inductors find application in the following: in tuning circuit, sensors, store energy in a device, induction motors, transformer, filters, and in chokes. These are areas where inductor find application. Let's look at the magnetic field energy of an inductor. We have earlier seen that in self-inductance is expressed by this, and we know that power is given as current times the induced EMF. If we take the rate of the change in work, the work done, to be P, the power times the rate of time, And if we simplify this for power, we'll have that the change in work done is equal to this. Let's integrate and see. Let's look at the total work done. The total work done to increase the current from 0 to I by integrating this expression, we will have the total work done to be given as equation 13. And this work done is equal to the energy stored in the inductor given by U when is carrying current I. So we can express that as equation 14. Equation 14 is the expression representing the energy stored in the magnetic field of the inductor when current I is flowing through it. Let's look at an example of how to use the expression we just derived. We have equation here, and we are to find the energy stored, the magnitude of the self-inductance, and the energy stored in the inductor. So we are using this expression. If we substitute that the self-induced EMF using this expression and substituting, we'll have it to be 25 volt. Then the energy stored in the inductor using this expression, we substitute, we'll have it to be 0.113 joule. Therefore, the energy stored in the inductor, a solenoid, is equal to 0.113 joule. So this is how to go about calculating the self-induced EMF and the energy stored in the inductor. Thank you for listening. Please subscribe to my channel for more videos. Like and share this video. Bye for now.